All right, this is a video for Trig practice 6.1 through 6.4 and just looking at number 7 when we have to solve for x in this case and give all values of x that make this equation true, and we're going to have x be in radians. Okay, so the first part of this is the goal is to always isolate a single trig function equal to some ratio. And I notice in part A, I've got sine of 3x in more than one place. One of them's squared and one of them's not squared. So I could think about it as a similar problem if, say I had y equal, or let's do z. Say I had z equal to sine 3x. Well, this is just really, initially, I'm doing 2z squared equals z. So how would I approach this just to start? I'd bring everything to one side and then factor out the z. And so I've got z equals 0 in this case. Oh, I forgot the 0 over here. And z equals 1/2. But then I'm just going to plug back in what that z was. And again, you don't have to do this z substitution. You could just bring the sine 3x over and recognize that both terms have sine 3x and just factor that out. But if you don't recognize that at first, sometimes a z substitution is helpful. Okay, so I've got sine 3x equals 0. So that's one equation I'm going to solve here. And the other is sine 3x equals 1/2. So I find it helpful to first think between 0 and 2 pi as I'm going around the circle. Where does, in this case, sine equal 0? So if I was just doing, again, between 0 and 2 pi, I would say it equals 0. And by the way, we're first going to solve for as if we had an equation sine theta equals 0. And so we're going to forget that I have 3x just to start. Eventually, I'm going to divide by 3 to solve for x, but let's just solve for what 3x is. In other words, what angle, when I take the sine, do I get 0? And I think, okay, I've got, it's 0 when y is 0, so 0, pi, 2 pi, and if I keep going around the circle, it looks like every multiple of pi, I'm getting sine to be 0. So I would say 3x equals, well, I can represent every multiple of 0 by, every multiple of pi by k pi. And I may just want to, on top here, write k is an integer, is any integer. Okay, and now I would just divide by 3. And so that's the solution for the sine 3x equals 0. I'm going to do the same for 1/2, but when I'm talking about an angle, when I take the sine equaling 1/2, I'm going to be within a quadrant. I'm not landing on an axis. Well, I know sine is positive in quadrants 1 and 2. So if I was just doing between 0 and 2 pi, I would do 5 pi over 6, not 5 pi over 6. That is one of them, but I wanted to start with pi over 6. The quadrant 1 angle is pi over 6. And the quadrant 2 angle is 5 pi over 6. And then if I went around the circle again, you know, more than 2 pi away, I would have 13 pi over 6, and so on. So, and then to get the other quadrant 2 angle, I would be adding 2 pi to this angle, and so on. Well, how can I represent that with k? Well, I can represent all the quadrant 1 angles by saying 3x equals pi over 6 plus 2k pi. So every time I go around the circle and hit that first quadrant angle that has a reference angle of pi over 6, I'm going to get 1/2 when I take the sine. And then I just need to divide by 3 Make sure to divide every term by 3. And let's do the same for, this was, remember, quadrant 1. Let's do the same for quadrant 2. So I would say 3x equals 5 pi over 6 plus every time I go around the circle. And then just divide by 3. So 5 pi over 18 plus, oh, this was 18, whoops, plus 2k pi over 3. So all my answers to this problem are here, oh, not there, here, and here. So I could represent when it equals 0 with just one equation. Where it equals a half, I had to use 2 different equations. So notice B and C, you don't have to do any algebra because there's a single trig function. It's already isolated. So I just have to solve for x. But we're always going to solve for whatever is inside the parentheses as a single entity first. In other words, we're just going to solve cosine, like cosine of theta equals -1/2, where theta is x over 2. So think about that. Don't get hung up on the x over 2 because we're going to deal with that at the end when we solve for x. All right, so when I think about cosine of what angle gives me -1/2, well, I know cosine's negative in quadrants 2 and 3 because it's where x is negative. And the reference angle, when I take the cosine of it, that gives me 1/2 is pi over 3 or 60 degrees. So the corresponding quadrant 2 angle would be 2 pi over 3. And the quadrant 3 angle would be 4 pi over 3. So just like with sine, in order to get all those as I'm going around the circle, infinite times in the positive or negative direction, I'm going to say plus 2k pi. And again, k is any integer. So that is totally acceptable answer. You will sometimes, however, see me be a little bit more lazy, or just, I guess it's debatable whether you could say lazy or concise. And instead of writing the answer with 2 different statements here, I noticed that 4 pi over 3 is coterminal to -2 pi over 3. So I can get all quadrant 2 and 3 angles by simply saying plus or minus 2 pi over 3 plus 2k pi. So often you'll see in my solutions I do that. Instead of doing 2 separate positive angles for quadrant 2 and 3, I do the positive quadrant 2 and the negative quadrant 3, which is coterminal to, in this case, to 4 pi over 3. And okay, so actually I'm getting ahead of myself. That was just what theta is, or what x over 2 is. So we're not quite done here. So we've got x over 2 equals this. And now solving for x, I'm just going to multiply everything on the right by 2. So I'm going to have x equals 4 pi over 3 plus 4k pi. And for the quadrant 3, I would have 8 pi over 3 plus 4k pi. Or if I wanted to do just the one line, it would be plus or minus 4 pi over 3 plus 4k pi. Either one's acceptable. So, or x equals that. Okay, so the last one, tangent. And again, in this case, notice that I don't have to do any algebra to isolate a trig function. It's isolated. And again, just think about first if you're solving tan theta equals -√3. And then we'll plug in what theta is, which is 2 pi x minus 1. But if I'm thinking of solving this, first thing again is I think of where is tangent negative, and it would be in quadrants 2 and quadrants 4. And let's just figure out what are the angles between 0 and 2 pi. Well, tangent of pi over 3 gives me root 3, so that's my reference angle. So I'm going to have 2 pi over 3, and the quadrant 4 angle is 5 pi over 3. Well, the interesting thing about tangent is, remember, it is positive in diagonal quadrants and negative in diagonal quadrants. So for tangent, I'm actually not going to use two different angles and say plus 2k pi, because notice these angles are pi apart from each other. So I really just need one statement to represent all angles, and I'm just going to say plus k pi. So in this case, I would do 2 pi over 3 plus k pi, because notice if k is 1, I get 5 pi over 3. And then I'm just setting this equal to what was inside the tangent and solve for x. So the first thing I'm going to do is, and this, by the way, is not a very pretty answer, but you just isolate x. So I'm going to add 1. Can't really combine the 1 with the 2 pi over 3. And then I just divide by 2 pi. So again, not exactly pretty, but so x is 1 over 2 pi plus 1/3. That one turned out kind of nice, plus k over 2. So definitely a weird answer, but that would be your answer for x in this case. So kind of the takeaways: when your ultimate sine function, when your ultimate equation is a sine function equal to a ratio, particularly if the ratio is something that corresponds to an angle that lands in a quadrant, you've got to represent those angles with two different equations. You just can't capture it in one equation. With cosine, you can represent it with two different, but notice that because of where they're positive and negative, you actually could do it with one equation and do plus or minus, whatever your preference, honestly. And then for tangent, because, well, as we even saw with the graphing, the period of tangent is pi, or it repeats itself every pi, we can represent the angles using one angle and just doing plus k pi.